In looking at vertical asymptotes, we were worried about values that were not in the domain. But for horizontal and oblique asymptotes, we're much more concerned with the behavior as the function as x approaches infinity and x approaches negative infinity. Since we're dealing with rational functions, remember we have two polynomials in ratio to each other, we need to consider the effect that the numerator polynomial and the denominator polynomial have on each other. For example, consider f of x is equal to 6x plus 1 over 5x squared minus 2x plus 3. Any function with a degree of 1 or bigger is going to increase in magnitude as x gets bigger. So as we go towards infinity, both of these functions, the numerator and the denominator, are going to get bigger. But what we have to consider with rational functions is which gets bigger faster. It's going to play the bigger role. In this case, the bottom function is stronger because it has a degree of 2. So as x goes to infinity, positive or negative in this case, the denominator is going to get bigger more quickly than the numerator. So we're going to be dividing by big numbers and the function will approach 0. However, if we consider this function, 6x squared minus 3x plus 2 over 3x squared plus 5x minus 17, notice the degrees are the same. However, as we move further and further away from the origin, the higher power terms get bigger faster than these other terms. So we can begin to ignore those because the biggest term starts to dominate. We can pay close attention then to just 6x squared over 3x squared. Notice these cancel and we're left with 2. This implies that the function f of x is going to go to 2 as x goes to positive or negative infinity. That's our horizontal asymptote. What if we have something where the numerator is bigger? We've looked at the denominator being bigger, them being the same in terms of degree. What if we have something like 7x cubed plus 2x minus 1 over x squared plus 4? Here, the numerator dominates, excuse me. So it's going to keep getting bigger and bigger. When there's a difference of just 1, this creates an oblique asymptote. To find that oblique asymptote, we divide these two and find the quotient. The quotient is the oblique asymptote. Let me try to spell that a little better for you. Or the slant asymptote. So that's if the difference is simply 1. What if the numerator has a degree that exceeds the degree of the denominator by more than 1? So for example, what if we had something like this? Here, that function is going to increase without bound and has no asymptote. So if the degree difference here is greater than 1, it's going to have no asymptote. This leads us to our theorem for equations of horizontal and oblique asymptotes. And what it says is, if we have this rational function and we have an nth degree polynomial on top and an nth degree polynomial on the bottom, I've listed here what we're going to call our leading coefficients, and we're going to assume it's already reduced, no common factors except for constants. Here are the steps for finding your horizontal and oblique asymptotes. If the numerator has a lower degree than the denominator, then the function's going to approach 0, and the axis is the horizontal asymptote. If the two are equal in degree, then the leading coefficients create the horizontal asymptote. If the numerator is greater by 1 value in degree, then the quotient of the two is the oblique asymptote. And if the degree of the numerator is more than 1, bigger than the denominator, then there is no straight line or horizontal asymptote. Oblique or horizontal. So let's look at some examples here. If we have something like x squared plus 1 over x squared plus 2x minus 15, the degrees are equal. So we just look at the leading coefficients, and the horizontal asymptote is going to be 1. Suppose we had x cubed plus x squared plus 2x plus 2 over x squared plus 9. Notice that n, the degree of the numerator, is bigger than m, and it's bigger by just 1. So there's an oblique asymptote. We would need to do long division here, and you would find that the oblique asymptote is y equals x plus 1. We're not worried about the remainder, only the quotient. If we have a rational function such as this, the denominator is bigger than the numerator. So this is going to play a more significant role than the top, which leads to the horizontal asymptote of y equals 0. And last but not least, if you had something such as this, the numerator is equal to the denominator plus 2 in this case, so there is no horizontal or oblique asymptote.